Now, welcome to our lecture, Fact and Power Quality. This is our 13th lecture. In the last lecture, it was discussed the shunt compensation and the requirement of shunt compensation with a different location. The first best location of the shunt compensation, ideal shunt compensation in the transmission line is the midpoint of the transmission line. So the advantage of midpoint shunt compensation, the power handling capacity uh, would increase up to the double of without shunt compensation. Second point we have discussed for the radial line, the best location of the shunt compensation at the end or near to the load condition. This is the 2 points which we have considered. And the third point is that the shunt compensation also reduces the oscillation in the system, and that oscillation is due to the perturbation. There may be the application of fault. All these things and conditions are there. And fourth point, the shunt compensation also improves the transient stability, and it is examined with the help of equal area criteria. Now, today's lecture is based on method of controllable VAR generation. Now, whenever we are connecting shunt devices or shunt fact controllers are there, either it should generate the reactive power or it should absorb the reactive power under different conditions. So there should be some method which control the VAR generation, or it may be absorber or it may be a generation. So simply we are calling as a VAR generation. So therefore the learning objective of today's lecture are understanding controllable VAR generation, identify the different method of variable impedance type, static VAR generation. This is important, is a static one, and understand the VI characteristic or VI area of different type of static VAR generators for the different methods. So there are two methods to generate the VAR. Either VAR means it is a voltage ampere is a reactive power. Okay. So type of generators are variable impedance type static VAR generator, means where we are able to vary the impedance. The impedance may be an inductive impedance or it may be a capacitive impedance. Definitely it is a static one. The system should be a static. Second is the switching converter type VAR generator. Now, there are two methods. First, we will discuss the variable impedance type static VAR generators. We know that by the definition, the capacitor generates and reactor or inductor absorb the reactive power when it is connected to the AC system. It's very simple. Whenever we are connecting anywhere a capacitor, definitely it is going to generate the reactive power, and when the inductor is connected, it is going to consume the reactive power. Just a minute so that we can draw a figure, so it become again simple. So it is our lecture. This is number 30, and it is a controllable VAR generator. Okay, so first we are going to discuss it is the static variable impedance. Impedance type static var generator. Okay, now when we are connecting a capacitor to the load, simply this is for the simple understanding so that we should understand very well. Suppose we are connecting a capacitor over here near to the load. It is going to deliver the reactive power required by the load, because load need active and reactive. Total kVA of the load is equal to the active power plus some reactive power. So this reactive power is delivered, the leading reactive power is delivered by the capacitor kVAR leading side. So the requirement of the reactive power or the requirement of apparent power from the source is going to reduce. Similarly, if a capacitor is connected near to the load or somewhere, it is going to consume the reactive power kVAR, isn't it? So there is a two differences. When it is connected a capacitor, it is going to generate, and when a reactor is connected or inductor is connected, it consumes the reactive power. So one is the generator, so we can call as a reactive generator. It is a generator because it generates, and here it is a absorber. It is the absorber. Okay, so this is the difference. So it can be connected with the help of some mechanical switch, or it may be a contactor. Number of contactors are there, and as per the application, as per the need, we can switch on the capacitor or switch on the inductor. So it is not a static, fully static one. Second method is that where it is called as a active power compensation. Say this is the load, and near to the load or say somewhere, we are going to connect a motor, that is a synchronous motor. Okay, and this is synchronous motor, it is connected, and the synchronous motor is excited. The DC excitation is controlled by any means, by some means. So under excitation it will consume. So under excitation it become a var absorber, because it consume the reactive power, so it become a absorber. And whereas when it is a overexcited, the synchronous motor, this is synchronous motor, okay, this is the synchronous motor. Okay, so overexcited, it become a var generator. Var generator, because it is going to deliver the leading reactive power to the load circuit. So either we can connect the capacitor, we can connect the inductor with the help of some mechanical switch, or it may be the contactors in sequence, and by on controlling that contactor signal, we can use switching on and switching off the inductor as well as the capacitor. The second method is a smooth control. It is in the stepwise step control. It is a step control, because either we are going to switch the capacitor of 10 kVR, 20 kVR, 30 kVR, or it may be some MVR in the higher capacity in the power system. Whereas the control over the synchronous motor means excitation control. Either the machine is going to work under lagging power factor, it may be work on the unity power factor as well as in the leading power factor. But the control over the power factor is smooth, so it is called as a active power compensation in the power system. But what is the disadvantage? the disadvantage is that it is a motor. It is some mechanical components. There is some wear, tears are there. Maintenance is needed, and the synchronous motor also consumes the active power. So, say for example, if I draw the vector diagram for that synchronous motor, say this is the uh, active energy. Say it is a kilowatt plus J kVAr is needed from the source. So it is the active power of the load. Say this is the initial power factor of the load is there, theta 1. Now this is the uh, synchronous motor, but synchronous motor also consumes some power. It is the active power, and it may work on the leading power factor or lagging power factor. As per this one, it is going to improve the say it is improve the power factor of load, but at the same time it having some capacity or its capacity of the uh, synchronous motor over this one. So it is a leading kVAr supplied by the motor. It is the active power of the motor. Therefore, the capacity or the kVA capacity of motor is equal to the kilowatt, say motor. So it is M plus J kVAR C reactive inductive power supplied by the motor. So simply, this discussion is only that it is the no doubt it is a static one, but the control is a stepwise. This is active compensation device in the power system. But as it is a rotating machine, so there is a wear and tear, some frictional windage losses are there, active power consumptions are there, and at the same time, the maintenance also we have to take the maintenance of the synchronous motor. So nowadays, instead of this one, the thyristors or the power semiconductor devices are there. It is a number of thyristors can be connected, and by connecting the number of thyristor, the thyristor is going to control with the help of delay angle, which we have learned in the power electronics, or their conduction angle by controlling the conduction angle or delay angle. Second is that it is a completely static one, so it acts as a static switch. Means when the your SCRs or some walls are there, power semiconductor walls are there, it is completely conducting, it become a switch and turn on and turn off by delay angle. So hence it is possible to control the VAR generation or VAR absorber. VAR absorber is an inductor, VAR generator is a capacitor. So as per the definition of IEEE, this is the definition by IEEE, and the second is the CIGRE. We can define, or one can define, a static VAR generator whose output varies as so as to maintain the control specific parameter, especially or for example, voltage and frequency of electric power system. So what we are doing with the help of this gate turn off thyristors or some thyristor walls, different type of power semiconductor devices, it is possible to change the um, uh, absorption, reactive power absorption or reactive power generation, isn't it? And therefore, it is defined as the static VAR generator or static VAR compensator. Instead of this one, static VAR compensator, SVC. SVC is the subset of statecom. It is there are different type of shunt compensations are there, which we are going to consider here. Okay, so thus the static VAR compensator SVC, so as to maintain or control specific parameters, uh, especially the voltage and frequency of the electric power system. The static, simply again, the static VAR generator is a self-sufficiently functioning device that draws controllable reactive current from alternating power source. So it is a self one. Second is that, and therefore we can have, instead of the say switching type or rotating type, we can use different type of thyristor, or the walls are there. Now the thyristors, say first we will take the example of, there are different type of static var compensators are there. Now these are the first one we can consider. It is the thyristor control thyristor controlled and thyristor switched reactor. So it is simply written as thyristor control. Uh, sorry, this is thyristor controlled reactor and thyristor switch reactor. So either it is a thyristor control. Control word means we are going to control the war in a smooth manner. And thyristor switch means either we are conducting the thyristor 100% or the thyristor make off, so it become a simple switch. So instead of using some contactor or mechanical switches, we are using thyristor wall as a switch and thyristor wall as a controllable device to conduct the current or to decrease the current in the inductor in such a way that it is possible to provide variable var absorption in the power system. These thyristor walls is in the rating of, which is available in the rating of 400 to 4000 to 900 or 9000 volt. Means one wall is maybe up to the, it can be written as simply in kV, 4 kV to 9 kV. Okay, this is the voltage rating. This is the voltage rating. This is voltage rating, whereas the current rating, it is from 3000 to 6000 ampere. It can handle safely ampere. So it is simply, we can say that 3 kA to 6 kA is the current rating. Current rating. So whereas our system voltage is very large, so what we will do is a very simple. Suppose the system voltage is very large, it's not a 4 kV, 9 kV, it is a 132 kV, 400 kVs are there. So number of thyristors to blocking the voltage of higher capacity, we are using number of thyristors are in series. Say this is the line, and there are number of, we can connect number of thyristor walls in the parallel, sorry, it is in the series, it is in the series to maintain the, or to blocking the number of higher voltages. Say it is a 9K, it is also 9K, it is also 9K. So similarly, there are, it may be a 10 to 20 number of thyristors are connected in series to maintain the higher voltage blocks. And similarly, if the capacity of current has to be increased, the number of thyristors are connected in parallel. So either it may be, it is connected in series to maintain the, or to increase the voltage up to the required value, or blocking the voltage uh, uh, maybe in some 132 kV, 400 kV. And to increase the current capacity or current handling capacity, the number of thyristors, they are connected, semiconductor, power semiconductor thyristors are connected in parallel. And this entire family, that is number of thyristors, those are connected in this one, it is called as a wall. And what is the requirement? The gate pulse which we are going to provide for each say thyristor one, it should be synchronized or simultaneous. What will happen? Suppose this SCR is conducting, this SCR is conducting, but this SCR is not conducting. So, for example, here, suppose it is the 9 kV, 9 kV, and 9 kV. So, this is conducting, and total voltage is going to apply over this one. Means total 27 kV is going to apply, and this is going to damage. So it is very much necessary that either the number of thyristors, those are connected in series or those are connected in parallel, it should be synchronously switching on and off, or it may be the delay angle. Whatever the gate pulse are there for controlling as a switch or controlling the conduction angle or delay angle, it should be a simultaneous. At the same time, if you are delaying by some time, the same time should be here, same time should be, and it is a simultaneous one. Otherwise, it will lead to a major problems over this one. So this is the very basic points which is related to the semiconductor walls are there, which we are using for the thyristor control reactor and thyristor control switch is there. Okay. Now, second point is that if the current in the reactor can be controlled from its maximum, that is thyristor become closed, or to zero when the thyristors are open. So this one we can do with the help of or by using some delay angle in this one. So current conduction can be controlled either in the switching manner or either in the in the step manner. Okay. Now we will have some look to the TCR, thyristor control reactor. Okay. So in thyristor control reactor, what would be the diagram? As we are using the shunt compensation, the meaning is that whatever the inductor or capacitor, it should be connected in parallel or in. So this is the line. Okay. And for our simplicity, we are, instead of drawing the number of semiconductor power semiconductor devices, those are connected in parallel for the requirement of line voltage, we simply represent a single wall is there. So this is the inductor whose responsibility to absorb the reactive power. So as it is absorbing, the current is going to absorb. So here we are using thyristor because we want in both direction conduction, positive at the negative half cycle. So this is the direction of current, and direction of current is IL. Inductive current is the function of delay angle or absorb or conduction angle, isn't it? Which is depend. So it may be acting as a switch, as a controllable switch is there. So this is the thyristor walls are there. Now, by controlling the gate wall, one more thing is that in the negative and the zero crossing of the voltage, the thyristor become off. So there is a self commutation in the thyristors one are there. Now, what would be the conduction mode of the thyristor? Okay, so we can understand with the help of some waveform. This is the, say, voltage, system voltage. Okay. Now this is the maximum crest of the voltage. This is voltage V. It is passing from its maximum value. And first we will consider that without any delay angle, the conduction of current. So we try to conduct the current without any delay. So this is the positive half cycle of the current. There is no delay at all. So we can represent as current IL. This is the current IL when delay angle alpha is equal to 0. Means there is no delay in the firing of this thyristor wall. Okay. So when there is no delay at all, this is conducting full current and this is the positive half cycle. And similarly, we can represent as a negative half cycle. But if there is some delay, then the current in the thyristor or the absorption is represented as this is the delay one. So this is the delay angle. This is the delay angle which already learned in the power electronics. This is the delay angle alpha. Okay. And now what is the conduction angle? So it is going to conduct up to both sides. That is from say it is 0, it is pi by 2. Here it is a pi. This is the value of pi. Okay, this represented as a pi. So this interval is the conduction angle. Say this is the conduction angle. So just we'll write for our simply to understand very well. It is the uh, firing angle or delay angle. Delay angle, and this is the conduction angle. Conduction angle. Now, by delaying the angle alpha, it is possible to control the conduction angle. Now, one more important thing which we have to remember in the this one, as we are trying to conduct after 90 degree. This is 0. This is pi by 2. It's a 90 degree. Means the conduction is after 90 degree. Then it is possible to have the current in the inductor is lagging by 90 degree. So it is going to absorb the reactive current or reactive power from the circuit. So what would be the switching angle? Basically the switching angle is going to vary from, means alpha is possible to vary delay angle from 0 is greater than 2. The alpha is smaller than pi by 2, 90 degree, isn't it? So up to this one, but from where it is going to start? It is going to start after 90 degree. So your conduction angle become the conduction angle. What would be the conduction angle? Here the conduction angle is equal to, what would be that? It is the nearly we can say that it is from this one, from pi minus alpha, isn't it? Is the conduction, and again there is a minus angle pi is there. So twice alpha will be there for the conduction angle, isn't it? So this is the very important point is that. So now suppose we want to control, means again we want to decrease the value of current. So we will increase the conduction, we will increase the delay angle. Say this is the voltage. So this is the voltage, and after 90 degree, we want to conduct the current. So it is there is a no delay at all. So when this is no delay, just like inductive current alpha is equal to 0, first case, isn't it? In the negative one, we have delayed some value. So there the conduction angle is decreases. So here the firing angle alpha. So this current we can represent I alpha is equal to say delay angle by some value alpha 1. Okay. So this will be the conduction angle. This will be the conduction angle 1. Now from this one, again we have increased the conduction angle, decrease the conduction angle. So here the conduction delay angle has been increased. So this current is I alpha at alpha 2, whereas the conduction 1 is again decreases. So here, if you decrease the conduction angle so on, the total current, or we can say that here we are going to decrease the current in step manners, and hence it is possible to control the reactive power absorbed by the thyristor control reactor, isn't it? So only by delaying the firing angle, the conduction angle go on decreasing, or vice versa, but the range is only from pi by pi minus this one, means after 90 degree it is up to that 90 degree it is possible to vary the current in the thyristor one. So if suppose we are not delaying any angle, so what it become? It become a simply switch. So thyristor reactor, thyristor switch reactor is without gate control. Without gate control, it become a thyristor switch. Either this value we are getting, or either we are getting the zero value in the current. So simply without any gate control, it become a thyristor switch, isn't it? Now, how to examine? It can be examined with the help of before going to this one, we just want to see the variation of current, inductor current, with respect to firing angle or delay angle. So here it is the firing angle, okay, and here is the current. IL is the current with the function of firing angle. Say this is 0. We are going to vary up to from, say it is 0 value to the 90 degree, isn't it? So here it is, we are increasing 10, 20, 30, 40 up to the 90 degree. And similarly, this the percentage current is 100%. It is a 50% and so on. That is a percentage. So when the angle is 0, this is the angle, delay angle is 0. This is some delay angle is alpha. Again, if you decrease, this is the delay angle, third delay angle. Means if you are increasing the delay angle, the magnitude of current conducted by the thyristor wall or the current through the inductor is going decreases, and hence the reactive power absorption also decreases. So as the reactive power absorption decreases, it is a controllable war absorber. So higher 0 the conduction angle, maximum will be the current. But as we increase the conduction firing angle, if you delay the firing angle, the current decreases. At 90 degree, there is a switch off. So it is a switch on condition and it is the switch off condition. This is the case. So if you are using 0 degree or 90 degree, means delay, then it is called as a thyristor control reactor. It can be understand with the help of, it's a VI area. This is the current. Sorry, this is the current I, current I. This is voltage. This is voltage. So thyristor control reactor, and this is thyristor switch reactor. We can represent to its maximum voltage. So V maximum. And similarly, this is current maximum. We can conduct up to the maximum current. And this is the line represent the controllable, and area under this region, it represent the controllable region for the thyristor controlled reactor. So it is a thyristor controlled reactor where it is BL maximum, it is going to occur over here. So where Vm is the maximum voltage, is a, or you can say that voltage, so just we'll write as a V max is the voltage limit, I max is the current limit, and BL maximum is the maximum admittance of TCR. Okay, and BL is the admittance of reactor. Admittance of reactor. So here, this is represent that area, this area represent the controllable war generation, because in the thyristor control, it is possible to change the firing angle, and by changing the firing angle, the conduction is angle is go on decreasing, and hence the current and ultimately the reactive power absorption. Whereas for the thyristor control, thyristor switch reactor, it is simply represented as, this is simply represented as, there is no hashing area, that area. So it is acting as a switch. It is acting as a switch. No doubt here is a Vmax and it is the Imax. And this is BL. It is represented by the thyristor reactor. So this is area represent the controllable war output or absorption or the generation, isn't it? And this is simply, it's a switch. So this is, can be say, just to give the some proper diagram. So is it thing is wrong? Okay. So this is the points which we have started. So there are different type of uh, static war generators, variable impedance type, thyristor controlled, thyristor switch reactor. This point we have discussed. The remaining point we will discuss later on, but just we want to see what is that this one. So here, see here, this is the things which we have already covered. This is the thyristor walls. It is thyristor walls. Once we call as a thyristor wall, there are a number of thyristors are connected in series for making the proper voltage, or it may be some number of thyristors are connected in parallel for proper current rating. But the condition is that all the thyristors should be fired simultaneously, isn't it? So this is the voltage and this is the current without any delay angle, alpha is 0. But if you increase the delay angle, the conduction area is gone decreasing, and hence the current also get decreases. For this is the positive half cycle, and this is the offset value for positive half cycle as well as the negative half cycle, isn't it? So this is just a replica, just it is a mirror image over this one. This is the maximum current, and this is the current is under control. Now, if you are going to control the firing angle, here there is no delay in the firing angle. It is as it is. So 100% is conducting. It act as a switch on. This is the switch on condition. But here we are going to control the conducting or firing angle. The firing angle delayed by this small value. So that this is the conduction in angle. This is the conduction one. Now the amount of current get decreases. In the next cycle, with the crest value of the voltage, with reference to the crest value of the voltage, the delay angle or the firing angle is delayed. So the conduction angle will be smaller, and so on. So the effective value of current is here is the maximum. It's a higher value. Whereas in the successive pulse of the voltage or successive phase, this one, the current is get decreases. So by controlling the firing angle, no doubt the firing angle after crest value or the maximum value of voltage, so it is lagging, isn't it? This is the point we should remember. We cannot vary the inductive current from here and so on. Otherwise, it will be the wrong. So this is in this way we can say consider the this one, reducing the current in the thyristor. So this represent the thyristor controlled reactor, and this is represent thyristor switched reactor. So here this area represent the controllable values, isn't it? And whereas we are not going to control, either it is going to conduct or it is going to switch off. So this is the representation of VI area of TCR and TSR. So the next one, the capacitor switching, we will see in the next slide. Thank you.